Thank you. Good afternoon, everyone. My name is Pern. I'm a software engineer at Google Privacy team. So today I'm going to talk about something different, not differential privacy, but about KHyperLogLog, which is a technique that we developed for estimating the re-identifiability and joinability of large data set at scale. So this is a joint work with multiple colleagues of mine, including Damien, who is also affiliated with ETH Zurich. So two questions that we often ask in privacy is whether the data set is potentially re-identifying and whether data sets are potentially joinable in a way that it poses re-identification risk. So to answer, the metrics to answer these two questions are relatively straightforward, but the challenge lies with scalability. Can the analysis scale to analyze huge data efficiently? So our approach to this is by approximation. And we have kind of designed KHyperLogLog to explicitly answer the two questions that we asked in the beginning. So before I jump into describing KHyperLogLog, I will first give a background on approximate counting. So these are a class of techniques that are memory efficient. They use compact data structure, also commonly known as sketches. The size of the sketches is often bounded and measured in the order of kilobytes. Approximate countings are often streaming algorithms, which makes them easily parallelizable, and they often come with a bounded error rate. One basic approximate counting algorithm is called the k-mean value, which is used for estimating the number of unique values that we see in a data stream. So the idea is simple. So for every value that we see in a data stream, we'll hash the value, and we'll keep the hash value if it is among the k smallest hash value. So note that we do not need a cryptographic hash function here, but it needs to be a uniform hash function. So to estimate the number of unique values that we have seen in the data stream, we can then extrapolate from the density of the k smallest hashes to the entire range of possible hash value. The error rate with a configuration of k equals to 2 power of 10 is around 3%, and it has a memory footprint of around 8 kilobytes, assuming a 64-bit hash function. So we can actually do better than this with HyperLogLog. So instead of keeping the 64-bit hash functions, HyperLogLog counts and keeps the number of trailing zero in the hash value. So the intuition is as such: if we have seen a hash value with a lot of trailing zero, which is quite unlikely in practice, then it is likely that we have seen a lot of unique values. So HyperLogLog uses M counters. For all the values in the data stream, it will first hash the value, and it reserves some bits of the hash value for identifying which counter it should contribute to, and the rest of the hash value for counting the number of trailing zeros. It has a very similar error rate as k-mean value, but notice that the size is smaller than that of needed by k-mean value. So the size, the memory footprint required is 1 kilobyte as compared to 8 kilobyte. So we can actually do even better with HyperLogLog++. So HyperLogLog++ introduced a sparse representation mode. In this mode, it keeps a simple map of the hash value rather than the M counters. So it is more memory efficient to do so when the number of unique value is low, and it actually gives better estimate as well. So I've talked about k-mean value and HyperLogLog, but knowing the estimate of number of unique value is not quite enough, and therefore we introduce KHyperLogLog to estimate the re-identifiability and joinability of data sets. So KHyperLogLog is a two-level counting algorithm. In the first level, it takes inspiration from the k-mean value, and for every entry in the k-mean value, it has an associated HyperLogLog sketch in the second level. So we actually implemented a variant of HyperLogLog sketch, which we call HyperLogLog++ half-byte. So as the name suggests, it is actually more memory efficient than HyperLogLog++. So take the example of estimating that we want to estimate the uniqueness of user agent string of our browser. The algorithm is simple. So first we will hash the pair of value, and we check whether the hash of the user agent is already existing in the sketch. If it is already in the sketch, we will simply update the corresponding HyperLogLog sketch with the hash of the ID. If the hash of the user agent is not in the sketch yet, we will check whether it is among the k smallest hash value. And if it is among the k smallest hash value, we will simply create an entry in KHyperLogLog. And we will simply purge the entry with the largest hash of the user agent if necessary. So this is a visual representation of a sketch of a KHyperLogLog, where in the first level we have roughly a KMV sketch of containing the hash of user agent, and each of the entry here has a corresponding HyperLogLog sketch that keep tracks of ID associated with individual user agent string. So from this data structure, one can see that we can easily estimate the uniqueness distribution using one single KHyperLogLog sketch. So specifically, we can tell what's the fraction of user agent that are uniquely identifying, what's the fraction of user agent that is used by or shared by multiple users, and so on. We can also plot the cumulative distribution. Here we have two examples here, and on the left, we have a situation where most of the users use some common user agent, and therefore we have a heavy tail here. And on the right, we have a situation where the user agent string is really identifying and unique for every user. So if we put together two different KHyperLogLog sketch, we can do some other stuff. We can estimate the similarity of the two data sets by estimating the containment matrix. Containment is simply defined as the size of the intersection over the size of A or B. And if we know the containment matrix, we can actually go one step further. We can check whether there is any joinability risk in such a way that there exists a pair of join keys that are also uniquely identifying two different types of data, which is something that we want to avoid in practice. Right, so we evaluated the performance of KHyperLogLog through experiments. Compared to the counterpart of exact counting, we find that the CPU performance of KHyperLogLog is consistently 1 or 2 orders of magnitude faster. And because it uses a bounded memory, it has a bounded memory usage, it allows us to scale to very large data quickly, efficiently. So with the configuration of k to the power of 1024, and m is the size, is the number of counter in the second level, with the configuration of m equals to 512, we are looking at the memory footprint of around 256 kilobyte for KHyperLogLog sketch. We evaluated also the accuracy of KHyperLogLog sketch in estimating the uniqueness distribution. Specifically, we prepared several test distribution using publicly available data sets, including one from Netflix and the US Census data. So as you can see on the charts here, we have two different distribution profiles. On the left, we have a data set that is more identifying than the one on the right. The uniqueness distribution estimated by KHyperLogLog is colored in blue, and the true distribution is colored in red. We find that the accuracy is pretty good. We evaluated also the accuracy of containment metrics. Here, for sets of equal sizes, we find that the estimated containment is typically in the tolerable range with plus or minus 5% error. But the estimated containment can be a little problematic for sets of highly unequal sizes. As seen on the graph on the right here, when the cardinality ratio is more than 5, we see that the error rate can grow more than 10% and keeps growing with the cardinality ratio. And we acknowledge that this is a limitation with the way we compute containment metrics in a way that we estimated the size of the intersection by inclusion and exclusion principle. But this is really an area that can use some improvement. In practice, we are using KHyperLogLog in production, and for every analysis run, KHyperLogLog is capable of analyzing petabytes of data, and we estimate various statistics using the sketches that are produced in offline. So the ability to estimate various statistics offline is really important, particularly for joinability testing. It will be highly infeasible if we were to sort of test for joinability of data set using the original data. So I'm kind of fast here. So in summary, we introduced KHyperLogLog for estimating reidentifiability and joinability at scale. There could be some approximation error, but in practice, we think that it is a rather useful tool for us to understand the characteristics of the data and to inform the decision makers when choosing a data protection strategy. We also find it to be particularly useful for regression testing, particularly for detecting data joinability due to occasional data logging errors. There could be multiple directions for future work. So although it is memory efficient, but KHyperLogLog still is rather CPU intensive in a way that we require to read the data once entirely. So we think that some innovation or some improvement to be able to handle joinability testing using sample data would be really interesting. And we also think that there could be more usage, or there could be more application of approximate counting in privacy-enhancing techniques. And that's all. Thank you.
Do we have any questions? So I'll get us started. So you presented some techniques that it sounds like it makes it easy to compute these privacy-related metrics, this uniqueness and joinability. But if you did not use your method, I imagine they're still computable, but probably not efficiently?
Right. So in our experiments, when using a counterpart of exact counting, we find that particular method can't scale to handle even a terabytes of data. And
in terms of the memory requirement, or?
Right, memory requirement.
Thank you for the talk. This might be a naive question, but for the containment metrics you showed, is it easy to see that the other techniques like HyperLogLog++ and everything will be worse off, or is there a trade-off that you get better accuracy or coverage but worse containment?
Do you mean that there could be some other metrics for computing similarity of data set, or?
Like, does HyperLogLog++ have higher variability in the metrics that you showed for your technique?
Whether HyperLogLog++ will actually perform better.
Yeah.
So essentially, we have computed containment using the first level, which is the KMV. So that is a good question. I think it is comparable, essentially because so it depends on how exactly you estimate the size of the intersection. And here, we estimate the size of the intersection using inclusion and exclusion principle, which then is about the same for both methods.
Thank you.
So one last question. So you presented joinability as something you don't want, but let's say we're in a situation where we do want to have good uniqueness, as in not good identifiability, but we do want joinability. Are those things actually possible at the same time?
Right. This is the other side of the coin. It's like if you have, imagine that you are a big organization where different teams produce different data, and sometimes you want the data to be joinable
Right.
and to be discoverable. So it could indeed be a very interesting applications where you create a sketch of all your data, and there is a repository that gather all the sketches, and you might want to find, if I have this data set, what additional data set can I join with?
Okay. Okay, there's one more question over there.
If you publish this sketch, you might be able to infer some information about the data sets. Did you look a bit at this issue? Because
right, right. And actually, our co-author Damien published a paper that that the sketch is actually not private, and so we still need to keep the sketches with good control and with short retention time.
So you think if you needed to add noise to avoid this inference, do you think the accuracy of the estimation will degrade quite a lot, or did you do some experiment on this?
Yeah. So Damien, yeah. So Damien actually has a paper on impact that says that it's kind of impossible, but maybe you could, if you come up with better ways to have a differentially private estimator. That could be very interesting. Thank you.
All right. Looks like we can thank Pern one more time.
Thank you.